well, welcome back. We're making our way through the end of the ethers and epoxides chapter. We've got one more mechanism to talk about. Broadly speaking, we've got one more mechanism to talk about for this chapter, and then we'll mention a little bit about thiols and how sulfur reacts in some of these with some of these how sulfur makes and reacts to form some of these functional groups. So last time we had talked about, ring openings for epoxides is where we ended up, and we had made the point that under basic conditions, the epoxide is going to ring open with the incoming nucleophile attacking the less substituted side of the epoxide, right? And so if we go back over here, right, this was the specific example that we talked about. We got an epoxide, we bring in a nucleophile, the incoming nucleophile is going to ring open from the less substituted side. And the other explicit point that I don't recall making explicitly is that the incoming nucleophile is going to hit from the opposite side of where the epoxide oxygen is there, okay? And so I didn't explicitly say that, but it's implicit with the idea that this is an SN2-like mechanism, right? Remember with your SN2 mechanisms, the incoming nucleophile always comes in from the opposite side of where the leaving group is, right? So pay very close attention to the stereochemistry of the incoming nucleophile and where the epoxide opens up, okay? And that's going to be important today also, okay? So there's your brief review. Basic conditions for ring opening, we have SN2-like mechanism, all right? So let's continue on then, and let's talk about what happens under acidic conditions. So we can go to the generic example also. Well, let me give this a title. Let me give this a legible title. So acid catalyzed ring opening. And then we could say of epoxides in there, that would be just fine. Hopefully I'm on screen there. If not, I'm just a disembodied voice, but that's okay too. So anyway, here is Mr. Generic Epoxide. Let me make that a little bit better. Sorry, it's pretty early in the morning when I'm recording this, and apparently I haven't had enough coffee yet. So there's a Mr. Generic Epoxide. Let's put this under acidic conditions. So the most simple of acidic conditions is where we just have some kind of strong acid that we dissolved into water. So we've got some H plus around, and we've got some H2O, right? This could be easily abbreviated as just H3O plus, but for our purposes, that's just fine, right? Okay, so remember one of the things that I had mentioned in one of the previous discussions was that typically when you see an acid, it's going to be used in the first step of the mechanism. It's not always the case. All right, okay, we have all those caveats, got it, right? But if we're on the exam and we're stuck and we don't remember, right, one of these kind of, cards that you have in your back pocket there as well, I know I have an acid around, can I do an acid-base reaction to get things going, okay? And it's not too much of a surprise. We talked about this in one of the other lectures also, right? The oxygens in ether compounds, and by extension epoxides then, right? They are partially negative still, and so a partial negative is going to find a positive there, and we're going to come and do some acid-base chemistry, right? So first step here, nothing too surprising, right? Negative attacks positive, so we protonate our ring. Look at that fantastic looking epoxide, and that is so triangular. All right, so there's that. And so now we're gonna have to spend some time here, right? Because we've created a problem, let's say. Now we've created an oxygen with a positive charge, okay? So now we have to deal with those consequences. And here's where things get a little bit interesting, right? So the question is, how do we get rid of an oxygen with a positive charge? How do we get rid of the positive charge on that oxygen? Well, we can't just give it more electrons, right? This thing is already saturated, right? It's got enough electrons around it, right? The lone pairs and everything. So we can't just give it negatives, right? That's not something that happens. So what we have to do is we have to break a bond and turn a bond into a lone pair, okay? So we have to break a bond and turn a bond into a lone pair. Well, what's probably the easiest bond to break? Well, the easiest bond to break is probably going to be between the oxygen and the hydrogen, right? Remember, everything is reversible, okay? There's I believe you guys probably talked about this in OChem 1, the idea of microscopic reversibility, right? You know, as you go forward, you go backwards, and equilibrium, and all this kind of stuff that's at play there, right? So, obviously, we could go back to where we started, but that wouldn't really progress us along our mechanism, okay? So, what I'm trying to set up for you guys is just how we break this down here, right? So, we have to get rid of a positive charge in the oxygen, right? So, we have to turn a bond into a lone pair, okay? So if we break this bond and turn it back into a lone pair, we end up where we started. So that's not the bond to pursue, right? So now we're just left with one of these two bonds here. Got it? So if that didn't make sense, rewind it for just a bit and see if you guys can follow along with my logic there, right? Now, in this particular example, both of those, right, both of these carbons here, and both of those bonds there by extension are equivalent. So it doesn't matter which one of those bonds we want to pick. But let's think here for just a second, okay? Because I'm right-handed, I guess, I'll pick and break this bond here on the right, okay? So if I do that, I'm going to draw this kind of, you know, oddly here for a reason. You guys will see why in just a minute as we continue the discussion, okay? So I broke that bond there, and I leave behind that charge here in purple, okay? Pause. What is bad about what I just did? Well, we got our good old buddy carbocation around. That's a very common intermediate that we see in a lot of mechanisms. So it's not unusual that we generate a carbocation, right? We're also under acidic conditions. Right? We've already got a lot of positives around, so adding another positive there is not really a bad thing, right? That's another one of these cards you guys can keep in your back pocket. Typically with an acid, we end up generating a cation, although you'll see an exception here in just a second, right? So, but anyway, right? So, but the problem here is that we generated a positive generated a carbocation as a positive, right, on a primary carbon. That's not going to happen, right? There's one or two mechanisms that we'll ever learn that really happens. And even then we have to have special circumstances, usually high temperature and something like that to kind of accommodate for the high energy is required to generate that positive charge there, okay? So that's a problem. So we need to do something about this. Well, here's the thing that is going to happen, right? So let's say here for just a second, let's talk about extremes. Let's say that we do generate this positive charge. Now, if we go back to an idea that we talked about in, I believe it was the previous lecture also, with intramolecular interactions, right? We have now a positive charge, and right next door, right, we've got something with a negative. So if we're just thinking about this in extremes, right, what could happen to help stabilize is that oxygen could send out a lone pair and reform the bond, and we get back to here. Then what's the problem? Well, we have the positive charge here, or the positive charge there on the oxygen. Do you guys see what I'm doing here? Right, we're talking about this idea of reversibility, right? To get rid of this positive charge, we can reform the bond to get back to here. But then we have the problem where the oxygen still has the positive charge, right? So then we break that bond and we get back to here, right? So we're kind of stuck in between these two options. And I could have just as easily picked this other bond there. I hope you guys understand this, right? So here's what happens under acidic conditions with an epoxide. The answer is somewhere in between these two extremes, okay? So let's see if we can depict this. Here's what happens with this. Let's pick green here, right, to kind of indicate the true, right, the true circumstances. So what happens is like this. Okay. And I'm going to write something down for emphasis sake here, right? And then we'll come back and talk about it. All right, and there's that. Cool. And let's put this in brackets. Okay. So do you guys see what's going on here? So the oxygen wants to break that bond, one of these two bonds, to get rid of that positive charge. But if it breaks that bond, then we have a high energy situation, we end up with a positive charge there. So that can't happen. So what it does is it basically tries to lift one of the, right, it tries to pull away from one of those carbons. And as soon as it starts to pull away, it leaves behind a positive charge, a partial positive, okay? And it can pull either direction, okay? And this is going to be important, right? Where this is the key part to understand here for acid catalyzed ring opening of epoxides. The oxygen is going to start to pull and leave behind a positive charge on one of the carbons, right? One of the two carbons here is going to end up with a partial positive charge here, not a full positive. A full positive charge would mean a carbocation. Then we're going to have rearrangements and shift and all that kind of stuff, right? So at the moment, we're only dealing with these partial positive charges here. Got it? Now, in our minds, when we're going through and we're analyzing this, right, both of these circumstances happen, and our assessment then is to say, which one of these positive carbons can handle that positive charge better, okay? Which one of these positively charged, or partially positively charged carbons can handle that charge better? And now we go back to the same ideas that we had for carbocations, right? How do we stabilize positively charged carbons? Well, we could talk about resonance and inductive effects and donations and all this kind of stuff, right? So all the same ideas that we have to stabilize full carbocations, okay? All those ideas that we have to stabilize full carbocations are valid to stabilize partially positive carbons also, okay? Now, in this case, these are equivalent, so it doesn't matter, okay? It doesn't matter. So either one can work, right? So the next step is that water comes in, right? So water's gonna come in, hit either one of those partially positively charged carbons. I don't know why I'm having trouble saying that all of a sudden. But anyway, right? And then we're gonna finally pop open the ring. So we have that. We have our water that came in here in black, right? And then we just have to finish by cleaning this up. So more water comes in and finishes cleaning this up. So let's just scroll up here to give myself some space to write. More water comes in and we finish things up. All right, so what does our final product look like? This in blue, I had this in black, and this was going in red here, okay? Fantastic. Good. So again, we end up with a situation where we have an alcohol next door to another alcohol, so a vicinal diol, okay? We have another SN2-like step here, okay? Except it's kind of like SN1 also, okay? Because we have to deal with the stability of a positively charged carbon, a partially positive, but still a positively charged carbon, okay? So we kind of have a SN1 and then followed by an SN2 type step, all right? So this is going to be important because remember, if we go back to what we started out this lecture and what we discussed last time, right? When we're talking about base catalyzed or base opening of an epoxide, it's all SN2. Our nucleophile hits the less substituted carbon, okay? Because we're purely working off of SN2. When we switch to acid catalyzed, we have to bring in concepts of SN1 and recognize SN2 is also at play here, okay? All right, so that's a lot of words. Let's put words into pictures, I guess, here, right? So now we're going to vastly complicate things. Cool. Let's just do this here for make it a little bit simpler, okay? So now we have an asymmetric epoxide, right? We've got a carbon here and a carbon here, right? That one's got other carbons coming off it, right? So we got a quaternary carbon there. A tertiary carbon, and then the other one's a primary carbon there, okay? Same idea. Let's H plus, okay, and H2O. Now would be a good time for you guys to pause and see if you guys can come up with the answer for yourself, and not just draw the answer, but draw the mechanism to get there, right? And not just draw the mechanism to get there, but also rationalize and explain it to yourself, right? Can you explain this mechanism to yourself? Or better yet, you know, if you're there in a, you know, if you've got your roommate around, or if you've got a buddy next to you, explain it to them, right? So anyway, right? So there we go. Let's take a look at what's happening. So if you want to pause here real quick, we'll come back and we'll start to work through this. All right, but it's acid catalyzed. First step, protonate. Okay. Go. Okay. Now we go into the dance of the epoxide, as I sometimes refer to it, but that's only me, and I'm a weirdo, so who cares, right? And what I mean is now we have to start to think, right, about what this epoxide wants to do, right? Remember, it's going to pull both ends, right? Or potentially. Right, this is kind of where the question comes from, right? So there's that, and let's finish this up, right? Finish this up. Okay, and so we'll pause here for just a second. Okay, so there are two options. We protonated, and then the oxygen's going to start to, right, pull from one side to the other there. And then when it does start to pull, it leaves behind a positive charge. So let's put some colors with this. Hopefully the colors come through. Let's do purple here, and then we'll do purple here, right? And let's see, black. I think black should show up. I hope these colors show up well on the recording there. I'll zoom in here just for argument's sake while I discuss this for just a bit, right? So here's our two options, right? We've got a positive charge on the purple or a positive charge on the black. So remember, our thought here is SN1-like, aka which one of those two carbons, the purple or the black, can handle that positive charge better. Okay? Primary, tertiary. Okay? So the tertiary carbon here in purple is going to be able to hold, right, or stabilize, I should really say, right, stabilize that partial positive charge better, okay? We have, right, donation coming from the other carbons around there, right, inductive and hyperconjugation and all these kind of ideas that we discussed with why tertiary is better than primary. Same idea here, okay? So this, right, is the, how do I want to say, the intermediate of sorts that gets attacked, okay? Although we don't really draw this in the mechanism, right? I'll clean this up in just a minute. I'm drawing it for you guys just for argument's sake here, right? If you want to draw it, and it's not like you're wrong, right? It's not like you're wrong, but you don't really see it drawn in the book or in textbooks and stuff like that, like this too often, okay? But this is the one that's going to get attacked, that one in purple there, okay? So let's do that, right? There's my purple, right? There's my purple right there. Let's bring in some red water here, right? So red water comes in, kicks that up, right? So we kind of move over here, right? We've got this, this, and finally, everyone's favorite step, the last step, where we just wrap things up. Fantastic. Cool. So the green bracketed part is there for, you know, the explanation and what's going on behind the scenes. If I asked you guys to draw the mechanism for this, right, you guys would just follow from here to here, from here to here, and then there to there, right? So that's really all we need to show for this, because under acidic conditions, the ring is going to open by having the incoming nucleophile attack at the more substituted side, right? At the more substituted. Oh my goodness, I forgot my methyl groups. Sorry about that. Didn't mean to cause those problems and that confusion. Methyl groups don't magically disappear. All right, there we go, okay? So that all being said, okay, so the under acidic conditions, the incoming nucleophile is going to attack at the more substituted side, okay? Fantastic. So as always, you know, there's wonderful practice examples in the book with this, okay? But there's the idea, and to get, you know, kind of your feet underneath it at the beginning, go ahead and draw these two right here. You know, stop and look at it and go, okay, which one of these two carbons can handle that positive charge better, all right? Okay, so one last thing, and then we'll kind of wrap this up, and that'll essentially be the end of this chapter. We have to talk about our, you know, let's say oxygen's next door neighbor, which is sulfur, okay? So we haven't really chatted too much about sulfur, but there are some things to recognize with it, right? So if we have an alcohol, right, that's an OH, right? If we switch to sulfur, right, we have a if I can spell, thiol, okay, and that would be just the sulfur equivalent of an alcohol, right? So remember, sulfur is right below oxygen on the periodic table, okay? So oxygen and then sulfur, right? And so the properties of sulfur are different, right? But there's very similar reactivity between sulfur and oxygen, okay? So, but there are some key differences we'll talk about in just a minute, right? So if we're talking about an alcohol, we've talked about this for quite a while now, there it is. If I talk about thiol, there a thiol is, okay? So what is one of the key important differences? Where thiols tend to be more acidic than the equivalent alcohols, okay? They tend to be more acidic. That's pretty important actually. For those of you who are going on to biochemistry, it's very important to recognize pKa's and kind of have a good understanding of what is more and less acidic in terms of functional groups, okay? Your sulfur, your thiols are going to be more acidic than than the alcohols are, okay? So ethers, right? This is what we've been talking about here, right? ROR. If we switch everything up to RSR, okay? We have the very cleverly named thioethers, right? So I guess they ran out of clever names at that point, but that's okay too. All right, so the basics are there. They talk a little bit about it in the book about some of the properties and the naming. I'm not too interested in, you know, sitting here and yammering on about the naming with you guys. Just read the little paragraph that's in there, look at the examples. Not too bad, okay? But anyway, so let's talk real briefly about how to make, or how we could make a thiol, right? All right, so let's say that I wanted to do this transformation here, okay? Let's say I wanted to do that transformation there. How could I do that? So we'd stop and we'd look at it, okay, and we do our analysis. We have a good leaving group. It's at a primary position. I do a substitution, right, at the position where the leaving group is initially attached, right? So primary leaving group, good leaving group, substitution happening at there, right? These are all ticking the boxes for an SN2 reaction. If we're doing an SN2 reaction, I have to have a good nucleophile, and a good nucleophile that adds an OH, or, you know, the easiest thing that we could do is just to put some OH minus in there, right? Because this is a darn good nucleophile that's going to hit the primary carbon, do an SN2, okay? Now we could pick, you know, potassium hydroxide, sodium hydroxide, cesium hydroxide. That doesn't really matter for us, right? We're doing chemistry on paper. We can kind of hand wave some of that stuff, okay? But hopefully, right, that's not too big of a shock for you guys. You guys understand what an SN2 reaction is. So if I want to take this exact same idea, and I'm really going to change things up now. You guys ready? Okay. So now, let's say I want to instead make a thiol here, okay? And you guys will see the point. I'll go ahead and get to the answer here. Right, so the same idea here, right? If we start out with a good leaving group in a primary position, we could add in the sulfur equivalent of hydroxide here, so sulfides, right? Hydrogen sulfide, and then bring in and make a thiol from that, okay? So there it is. In fact, this is going to be an even better reaction than with the hydroxide. Okay? Now, we could, this isn't OChem 1, so, but I'll just very briefly mention, right? This is a much better nucleophile than hydroxide is. It's not that hydroxide is a poor nucleophile, it's just that it's also a strong base. Okay? Strong bases and weak acids and, you know, weaker bases come from stronger, right? There's all this idea that's kind of going on behind the scenes, right? And it all comes down to how negative is that negative, okay? Is it spread out? Is it localized? And all these kind of things that come along with that, right? But the point being this, sulfurs with a negative charge are excellent nucleophiles. They will prefer to go through substitution mechanisms rather than eliminations, okay? And so we could kind of expand this out to where we get into the, you know, let's say the danger zone here for hydroxides, right? Where if we try and do an SN2, right? If we try to do an SN2 on a secondary here, right, we'd start to have some competition with elimination and all that kind of stuff. Really not going to be a problem though if we use our sulfides here. Substitution happens pretty readily there, okay? And it's a, you know, if you're asking the question why, or I don't understand that, or that doesn't make any sense, or what am I doing with my life, right? Then go ahead, right? Send me an email, or, you know, look it up, or whatever you need to do, but make sure you can answer that question. It's a very, very, very important, very important question. Why do sulfurs prefer to go through substitutions, and why am I saying that they're excellent nucleophiles, that kind of stuff, okay? But anyway, so there we can make thiols pretty easily. Now, you know, I made the point that, you know, oxygen and sulfur are very similar, and they are. That doesn't mean they're completely going to react in the same way. Something that's important biologically, I'm not going to talk about it too much, but we can oxidize thiols to make sulfates, okay? And in fact, if you're working in the lab and you're doing any kind of sulfur chemistry, one thing that you'll notice very quickly is that thiols stink like crazy, right? And so the way that we get rid of those smells in the lab is we oxidize them typically with a bleach solution. It turns them into sulfates. The sulfates aren't really going to smell at all, right? But we can also make disulfides, right? If we put these under certain oxidizing conditions, we can make disulfide bonds, right? And then we can break disulfide bonds. That's very important when you're dealing with biochemistry, right? Denaturing enzymes and disulfide bonds hold things together in tertiary structure, all this kind of stuff, okay? So, and they've got a couple brief mentions of that in the book itself there. So if you're interested in that kind of stuff and want a little heads up, you know, go through and read through that kind of stuff here. Not too relevant for us, because once you make a disulfide, I mean, it's useful to link together sulfurs, but it's a little bit outside the scope of what we want to do, at least in the second semester of OChem, right? If we had an advanced OChem course, then we could come back and we could talk a little bit more about those, but I think for the moment, I'll just kind of leave it to the book at this point, okay? But the last thing we want to do is talk a little bit about thioethers there, and that's going to be kind of, again, a good review for what we learned about with ethers themselves. And remember, one of the key important steps that we learned for ethers was how to make asymmetric ethers, right? And we talked about the Williamson ether synthesis. Do you guys remember what the Williamson ether synthesis was? Okay, I gave you guys a quick second there, maybe pause and think about it, right? So remember a Williamson ether synthesis, what we did is it was in 2 steps, okay? The first step is we deprotonated, right? We deprotonated, right? So we added some kind of base in there, okay? Let's do green, right? Just to spice things up here, right? So we put in some kind of base. We'll come back and talk about this in a second, don't worry, right? And then in the second step, we put in some kind of alkyl halide, okay? So the base deprotonates to make a sulfur with a negative charge, very good nucleophile, and that very good nucleophile reacts with our alkyl halide, and right, we do our asymmetric synthesis there, right? Or we end up forming our asymmetric ether, okay? And so our product here would be that. What is our base? Well, we could use something like sodium hydroxide in this case, right? Just because of the nature of the acidity of a thiol, right? We can use something like sodium hydroxide. Is that the only base we could use? No. You could pick pretty much any base that you want in there, okay? But the point being, right, So this generic setup here, right, some kind of base with an alkyl halide, you can make a thioether or you could just make an ether also, right? So that's our Williamson ether synthesis, one of these important things that we learned in this chapter. Okay, mechanism's the same, right? We do a acid base followed by an SN2 reaction. All right, but that's it. That's the end of chapter 13, at least for what I wanted to talk about with you guys. Definitely go through, take a look at the end of chapter problems in there, right? You guys have to, make sure that you're following along and working through some of these examples, right? So please, please, please spend your time to do that. If you guys do have any questions, don't hesitate to reach out to me. Be happy to answer anything I can along the way. All right, I'll see you guys next time. We'll launch into, I believe, it's going to be chapter 16 next. If I have my, yep, it looks like we're going to head over to chapter 16, where we'll talk about pi systems. All right, I'll see you guys next time.